Hello, my name is Aryan. This is my Lab 1 for Physics 2212 at Georgia Tech. First, I'll introduce the system and its surroundings and cover some key concepts for the lab. Then, I'll go through the observations and calculations conducted. Next, I'll introduce the computational model and then compare the results of the experiment with the computational model. Finally, I'll answer some discussion questions. The main objective for this lab is to determine the interaction between clear tape pieces and other objects, and also estimate the charge on the pieces of tape. We'll also determine the excess electric charge on each of the charged tapes and determine the change of charge due to transfer of electrons. We'll then try to simulate the interactions using a computational model on GlowScript. The system for this lab is a tape, and the surrounding includes the other tape as well as the earth. Some key concepts for the lab. First, we need to know the electric force between 2-point charges, which is given to us by the Coulomb's law. The force between 2-point charges is directly proportional to the product of the two charges and inversely proportional to the distance between them. The K is a Coulomb constant, which is equal to 9 into 10 raised to 9. The electric field due to a point charge is given by the formula 1 over 4 pi epsilon into Q over R squared into R hat for a vector. The force due to this point charge exerted on another particle is equal to the electric field into the charge. The force of gravity is given by F is equal to mg. Some key observations. The pieces of tapes are repelled by each other. The repulsion force was larger than the force of gravity. In fact, the upper tape was repelled by over 4 centimeters in our experiment. The tape was attracted to the negatively charged block, which confirmed that the tape was positively charged. The tape also was attracted to my hand. Some key calculations. Keep in mind that we have ignored the air resistance for this experiment. The net force on the upper tape is equal to the sum of the gravitational force and the repulsive electrical force due to the bottom tape. These two forces are equal in magnitude but act in opposite directions, giving us net force equal to 0. Hence, we can equate mg is equal to 1 over 4 pi epsilon into the product of the charges divided by d squared. This gives us the charge of the upper tape to be 2.3 into 10 raised to minus 9 coulombs. The force diagram is given on the right for reference. The number of electrons is given by the total charge of the piece of tape divided by the charge of a single electron, which is 1.6 into 10 raised to minus 19 coulombs. This gives us approximately 1.456 into 10 raised to 10 electrons. To calculate the total number of atoms, first we compute the total tape area, which is length into width, then divide this by the average area of one atom, which is 1 into 10 raised to minus 20 meters squared. This gives us approximately 3.6 into 10 raised to 17 atoms. Using the previously mentioned formulas, we can then create a computational model on GlowScript. The charge of a proton is positive 1.6 into 10 raised to minus 19 coulombs. The mass of the tape is 2 into 10 raised to minus 4 kilograms. The scale factor is set to 1. The charge of the upper tape is set to be 2.3 into 10 raised to minus 9 coulomb, and the charge of the lower tape is also set to be 2.33 into 10 raised to minus 9 coulombs to make the experiment fair. The first function calculates the electrical force while accounting for the gravitational force as well. The second function does not account for the gravitational force. In order to calculate the strength of the electrical field, we can then divide the force by charge. This gives us the electrical field. The results for the computational model are shown on the left. The first one accounts for the gravitational force, while the second one does not account for it. In order to understand the results of the lab, we must acknowledge some key assumptions and approximations made while conducting the lab. The air resistance was ignored while simulating the computational model. The net force of the tape only accounted for the force of repulsion and the force of gravity. We also assumed the pieces of tapes to be point charges. This meant that all of the charge was concentrated at the center of the tape. Each of the upper tapes was also assumed to have the same amount of charge, resulting in the same amount of repulsion. What if the electrons had a positive charge and the protons had a negative charge? What would be the changes in observations made during our experiment? The pieces of tape gain a charge through the transfer of electrons. Since the same amount of electrons are being transferred, or at least that is assumed to be so, they would gain the same amount of charge, just the opposite sign. And since like charge is repelled, there would still be repulsion observed, and therefore there would be no changes seen in the observations for the experiment. Next, why is it important to handle the charged tapes as little as possible? What happens when charged tapes come in contact with our hands and other objects? Well, handling the tapes allows electrons to flow out of the tape and into our hands. By handling them as little as possible, we are able to preserve the experiment to a more accurate degree.